Hey everyone, welcome to today's Explainer. We are jumping right into one of the most incredible leaps in modern transportation, the birth and global expansion of high-speed rail. We're going to treat this like a fast-paced lecture, tracking the evolution of these absolute engineering marvels. We'll start with their genesis in Japan, a country that literally reimagined what a train could even be, and then we'll track how that sparked a massive revolution across Europe. This is a story about battling geography, pushing the very limits of physics, and forever changing how human beings connect.
To keep us on track, here's our roadmap for today. 1. The birth of bullet trains. 2. France enters the race. 3. Germany's ICE network. 4. Italy's Direttissima and Pendolino. And finally, 5. Comparing global network performance.
Okay, let's dive right into Section 1, the birth of bullet trains.
When we talk about high-speed rail, post-World War II Japan is the undisputed pioneer. I mean, they were the very first to look at their existing railways and just say, nope, we need an entirely new, dedicated system. Fun fact, the term bullet train, or danganresha in Japanese, was actually coined way back in 1930, mostly because of the proposed shape and speed of the trains. But it wasn't until 1956, right in the middle of Japan's post-war reconstruction, that feasibility studies for a Tokyo to Osaka line really kicked off. At the time, their conventional lines were absolutely maxed out, and trains were creeping along at maybe 80 kilometers per hour. So Japanese engineers made this huge technological leap, aiming for an unprecedented 250 kilometers per hour. That dream became reality in 1964 when the Tokaido Shinkansen opened, perfectly timed for the Tokyo Olympics. And they didn't just stop there, pushing all the way to magnetic levitation tests in 1997.
Now, those early Shinkansen running on dedicated lines weren't just about showing off. They were built out of pure necessity. Japan's conventional network ran on a narrower gauge track, and those lines were packed to the brim. Plus, if you know Japan, you know the terrain is intensely mountainous. Trying to upgrade those old winding tracks? Yeah, that just wasn't going to happen. So they had to lay down brand new, straight, standard gauge lines capable of handling immense speeds right through that tough geography.
And man, did that decision pay off. 4.5 billion. Let that staggering number just sink in for a second. That is the total number of passengers carried by the Tokaido Shinkansen line alone, making it the busiest high-speed rail line in the world. To give you some perspective, this single route has moved more people than all other high-speed lines in the rest of the world combined. Talk about a massive human impact from an engineering marvel.
Moving right along to Section 2, France enters the race. So Europe is watching Japan's massive success from afar and thinking, okay, we really need to catch up. France actually started their trials in 1967 using a gas turbine TGV concept. But the real game changer happened in 1976 when a brand new 410-kilometer line between Paris and Lyons was officially approved as a project of public interest. Fast forward to September 1981, and President François Mitterrand inaugurates the Southeast TGV line. This was completely revolutionary for European travel. It slashed the journey time from Paris to Lyons from a sluggish 4 hours down to just 2. Almost overnight, it cemented the TGV's dominance across Europe. That first French high-speed train, the TGV Sud-Est, was an absolute smash hit. Thanks to those slashed travel times, it quickly built up an annual ridership of 15 million people, which rapidly skyrocketed to 20 million. France had essentially proven that yes, the Japanese model could be adapted and absolutely thrive on European soil.
But the French engineers, they were always pushing the envelope, testing exactly what steel wheels on steel rails could actually handle. In 2007, a TGV train hit a mind-bending 574.8 kilometers per hour. That is an incredible, standalone achievement. To this day, it remains the unbroken speed record for conventional high-speed rail. Just a massive testament to how far they push the boundaries of the tech.
Now, what's really interesting is that the innovation didn't stall out there. The French train maker Alstom poured 10 years and 100 million euros into a massive leap from the standard TGV to a system called the AGV. See, a standard TGV uses power cars at the ends to pull and push the trailer coaches. The AGV, though, is a modular concept. It groups cars in threes and is built to operate at a blistering 350 kilometers per hour. Inside the rail industry, this modular, high-capacity design was literally compared to the creation of the Airbus A380 jumbo jet, a real game-changer.
All right, shifting gears to Section 3, Germany's ICE network.
Germany watched the French TGV take off, and they decided to jump into the high-speed era themselves about a decade later, but they faced a totally different set of challenges.
They officially kicked things off in the summer of 1991, launching the first Intercity Express, or ICE trains, on lines between Hanover and Würzburg. By 1998, they rolled out the ICET. Now, these were tilting trains, which was a brilliant workaround. It drastically improved passenger comfort and shaved down journey times, even when they were navigating rougher, older, classic routes that hadn't been fully rebuilt.
Those early iterations, like the ICE-1, were pretty conventional in their layout. They relied on traditional power cars at the front and back of the train, kind of like the original French TGVs we just talked about. But Germany was about to pivot to a radically different design philosophy. By 1999, Germany introduced the ICE-3, which completely championed the concept of the multiple-unit train. So instead of having a heavy locomotive hauling everything, the traction equipment is distributed over the full length of the train. The ICE-3 powered every second vehicle in the set. This gives it incredibly fast acceleration. And here's the best part for the riders. Because all that bulky electrical gear is hidden under the floor, it frees up a ton of space. They even put a passenger lounge at the very ends of the train, giving people a completely unobstructed view right out the front windshield.
Let's head south for Section 4, Italy's Direttissima and Pendolino.
While France had the luxury of building long, straight lines across relatively flat countryside, Italy was staring down some monumental geographic hurdles. Take the Rome-Florence Direttissima, their main trunk line. They started building it in 1970, and it took an excruciating 20 years to finish, finally wrapping up in 1992. But wow, the payoff was enormous, cutting the travel time between those cities from 3 hours down to just 1. And because of their mountainous terrain, Italian engineers leaned heavily into tilting train tech early on, running trials with the Pendolino at 250 kilometers per hour as early as 1978.
So the crucial point here is perfectly highlighted by the Bologna-Florence bottleneck. When Italy started work on this line in 1996 to cut through the Apennine Mountains, they faced a literal wall of rock. Out of a 79-kilometer route, an astonishing 72 kilometers had to be built deep underground inside tunnels. It was an absolute engineering nightmare, and because of that, it became one of the most expensive railway lines ever built anywhere in the world.
Naturally, this harsh geographic reality heavily shaped Italy's rolling stock. They started off with the ETR 450 Pendolino, that first-generation tilting train built by Fiat. But as they completed those dedicated lines with the massive tunnels, they shifted to the ETR 500. This was a non-tilting, captive variant built specifically for those new, fast stretches. Eventually, they rolled out the ETR 460 and 480 series, which evolved to offer really nice luxury amenities, like full restaurant facilities for the passengers.
Let's move to our final section and see how this all builds together. Section 5. Comparing global network performance.
We've looked at the pioneers and we've seen the huge geographical headaches, but how do these networks actually stack up against each other in everyday operation? Well, this brings us to some frankly terrifying physics. There is a massive operational difference between running trains in the open air versus in high-speed tunnels. Picture this: 2 high-speed trains passing each other in opposite directions inside a confined tunnel. They can create a combined closing speed of 700 kilometers per hour. The aerodynamic pressure shifts from that are so incredibly violent they can literally shatter the windows of the train. Because of this, countries forced to rely on heavy tunneling simply must enforce severe speed limits just to keep everyone safe.
And that physics lesson completely explains the stark contrast in performance across these networks. Geography dictates speed. Japan and France run their trains on dedicated, mostly open-air tracks, easily hitting average speeds of over 250 kilometers per hour. But look at Germany and Italy. Because they are dealing with so many tunnels and those window-shattering pressure risks we just talked about, they're forced to slow way down. In fact, a conventional British railway running on open tracks actually averages a faster everyday speed than Italy's highly advanced high-speed network. All because the Italians are restricted to 165 kilometers per hour while navigating those massive, expensive tunnels.
Which leaves us with this final thought. What began in Japan as a desperate scramble to fix overcrowded tracks exploded into a globe-spanning engineering arms race. We've watched nations blow past 500 kilometers per hour, bore massive holes through solid mountains, and entirely reinvent the shape of the train just to cheat the wind. So as our demand for speed grows and as engineers keep waging war against geography, what is going to be the next major leap in connecting human populations? It's a massive puzzle, and one that brilliant minds are trying to solve on drawing boards right now. Thank you so much for joining me for this explainer. I really hope it gave you a whole new appreciation for the absolute marvels moving beneath our feet.